Welcome to this diploma program, Physics video summary. This time talking about 4.4 wave behavior. And in this slide we're going to talk about three different wave behaviors: reflection, refraction, and total internal reflection. Reflection is simply the fact that a ray coming into a surface will have the same angle of incidence to angle of reflection, where angle is measured relative to the normal, which is this imaginary line at 90 degrees to the surface. However, refraction is when we're going between two optically different media, for example air and glass, where the wave travels faster in air than to glass, so you have this apparent bending towards the normal of the ray, and you can find the angle given the wave speeds or the refractive indices, where the refractive index of a medium is its speed relative to the speed of light, c. Remember, c is 3 times 10 to the 8 meters per second. Nothing can travel faster than it. And because the wave slows down in medium 1 or medium 2 compared to 1, you see this fact that angle 2 is also going to be smaller. Now, if we reverse the ray and make it go from glass to air, then the angle of refraction is going to be larger in air than in glass, and at some angle called the critical angle, we will have a angle of refraction equal to 90, after which point the ray will be totally internally reflected inside the glass, which is the behavior which is used in laser optics and laser fibers in order to transport communication long distances. Carrying on this topic, we're going to talk about the phenomenon of diffraction, and that is the apparent spreading out of waves around objects or through a slit. So I'm going to show three examples here. Example 1 is diffraction through a slit, a single slit. Example 2 is diffraction around an edge, and example 3 is diffraction around an object. So what happens, and what's common for all of these is, for diffraction to happen, the size of the slit should be approximately equal to the wavelength of the wave. Size of object should be the same size as the wavelength. So when this planar wave arrives at the slit, what happens is it apparently spreads out, so it goes and brings a planar wave to a circular wave. The wavelength will still be the same, but we'll have the wavefronts will be semicircles instead. At the edge, this part of the wave will still be planar, but this part of the wave will be curved. And around the single object, we'd have planar waves either side, but then the wave would bend around this side, and it would also bend around this side. Now let's finally talk about path difference interference and two-slit interference, because they are all related. By path difference, we mean the difference in the distance at a certain point between two sources of waves. So here we have two sources of waves, A and B, and they both arrive at point P. The path difference is simply the difference in the distance the wave has had to travel from B, and the difference minus the distance that the wave has had to travel from A, or BP minus AP in this case. If it so happens that the wave at P arrives in phase, i.e. a crest meets a crest and a trough meets a trough, they will interfere constructively to give a larger displacement. In this case, the path difference has to be an integer number of wavelengths, integer whole number of wavelengths. However, if at P the wave's crest meets the other wave's trough, i.e. they are out of phase, they will interfere destructively, and for this to happen there has to be an integer half number of wavelengths. So in this case it will be the path difference will either be a half a wavelength, 3 half wavelengths, or 5 half wavelengths. Now if we were to just switch to see a simulation, this is from the great website PhET Simulations. Here is the pattern produced by a single source of waves. It's a dripping tap on a ripple tank. Now let's introduce a second source and see what interference pattern we get. So note, we have some parts of, let's just pause it, we have some parts of the wave which are a lot brighter and darker than others. That's where we have constructive interference. And we have these parts of the wave which are slightly dimmer. That's where we get destructive interference. If I increase the separation of the taps, but have the same frequency, you see I get a different pattern. The fringes are slightly closer together. So in this case, the red lines will be everywhere where we have constructive interference, where there's an integer half number of wavelengths. Here the path difference will be 0. Here the path difference will be 1 wavelength. Here the path difference will be 2 wavelengths, and so on. And the blue lines will be everywhere where we have destructive interference. Now, if we were to pass planar light through a double slit, we actually see the same pattern as if we were to have 2-point sources of light, because what happens is, as the light passes through each individual slit, it diffracts, and if we observe the light at the screen, we see patches of bright and dark, or fringes of bright and dark, which correspond to where we see a bright patch, it's where we have constructive interference, and when there's a dark patch, there's destructive interference. So the double slit interference pattern is very similar to the two-source interference pattern because the planar wave diffracts around the slits. And we define the distance between the slits as d, little d, the distance between the slits in the screen as big D, the wavelength as lambda, then the fringe spacing, i.e. how far these are apart, little s, is given by lambda big D over little d. So by decreasing little d, we get a larger fringe spacing, and by increasing either wavelength or the distance between the slits in the screen, we have larger fringe spacing.